I am super excited to be your guide today as we begin this unit on complex numbers. Today we're going to be learning about the imaginary number, and in this whole unit we're going to be learning that the imaginary number is useful for more than just finding solutions to the quadratic formula. There's going to be a lot of really neat and unexpected stuff that we'll learn in this unit, but I may be a little scary, so let's go ahead and take a deep breath first, and let's begin. So in this lesson, we're going to be learning about how to perform basic operations with imaginary and complex numbers. Now, I can probably assume that most of you have heard of the imaginary number before, you kind of know what it is, but I just want to make sure, so we're going to do some quick definitions here. So the imaginary number, I, satisfies I squared equals -1. In other words, when you square this imaginary number, you're going to get -1. Put that in other terms, I is effectively the square root of -1. Okay? That may be troublesome if you've got issues with that. I actually did an intro video before this one where I addressed some concerns that you might have about that one. But I'm going to assume at this point that you trust me on that and that you're ready to move forward and you're sort of laying down your concerns about there being a square root of -1. So a complex number is a number that can be written in the form x plus iy, where x and y are real numbers. In other words, a complex number is basically a number that has a real part and an imaginary part. And those are actually considered to be mathematical terms, right? If you have a complex number, z equals x plus iy, the real part of z, which is denoted re of z, is equal to x. It's equal to that part right there. And the imaginary part is the number in front of the I. So just to be very, very clear here, if z was 5 minus 17i, then the real part of z would be 5, and the imaginary part of z would be -17. You don't include the I here, because you're already saying that it's the imaginary part. You're really just giving the real number that's being used to sort of denote the imaginary part. One more thing that I might mention here, and it's probably something that you already know from when you learned the quadratic formula in the past, but just because we defined a new number for the square root of -1 does not mean that I also need a new number for, the square root of -9. If someone asked you for the square root of -9, you could really just see this as the square root of -1 times 9. In other words, the square root of -1 times the square root of 9. And we know that the square root of 9 is 3, and we now know that the square root of -1 is I, so this would just be 3i. So it's not like introducing one new imaginary number means that I need tons of new ones. We can use this idea of a complex number, of multiplying a real number next to I, to sort of help us to express other imaginary number concepts. So now that we sort of have a basic understanding of what complex numbers are and what imaginary numbers are, we want to move in and talk about operations. How do we add and subtract complex numbers? Well, the good news is that it's actually really easy, right? Adding and subtracting complex numbers is you just combine the real parts with the real parts and the imaginary parts with the imaginary parts, right? It's a little bit like combining like terms in polynomials. So I've got 3 examples here that all use the same complex numbers. I'll go ahead and go through the first one with you, and then you can do the second 2 on your own. So if you're given that w is 3 minus I, one complex number, and z is 1 plus 2i, how would you figure out w minus z? Well, what you would do here is you would do 3 minus I minus, and then z is 1 plus 2i. And you'll notice that I put parentheses around both of those things because this thing is effectively one number, and this subtraction is going to need to apply to both of them. So when we do this, 3 minus I minus 1 minus 2i, and then it's just a matter of combining like terms. 3 minus 1 gets me 2, negative I minus 2i gets me minus 3i. Yay, we did it. So I'd encourage you now, pause the video, make sure that you can work through these other 2 examples on your own, and I'll work through the answers here in just a moment. All right, so for this next one, let's see here, we would do 3 times 3 minus I plus 2 times 1 plus 2i. Can work these out by distributing. 9 minus 3i plus 2 plus 4i. And then just like we did in the previous one, I'll put together the real parts to get 11, and I'll put together the imaginary parts to get plus I, and there's our answer. For the final one, I would have 4 times 3 minus I minus 5 times 1 plus 2I. Again, we distribute these. 12 minus 4I minus 5 minus 10I. The real parts come together to give me 7. The imaginary parts come together to give me negative 14I. And there it is. Adding and subtracting complex numbers is nothing difficult at all. The next operation we'll talk about is multiplying complex numbers. Turns out this is also pretty easy. Slightly harder because we have to combine our knowledge of binomial multiplication with the definition of the imaginary number. So as long as you're comfortable and can remember that I squared is negative 1, we're going to be just fine here. Right? So if you were asked to do W times Z using these complex numbers, W for us is 5 minus 3I, Z is negative 2 plus I. So we're going to take this and multiply these, and foil these just like we would anywhere else. 5 times negative 2 gets me negative 10. 5 times I gets me plus 5I. Negative 3I times negative 2 gets me plus 6I. And finally, negative 3I plus I gets me minus 3I squared. Okay. We can see here that these are both imaginary numbers, so I could combine those. I now have negative 10 plus 11I. But the thing I want to focus our attention on is right here. Right, negative 3I squared. Well, we know that I squared is negative 1. So what I can do is I can replace this I squared part with negative 1. So I'm going to have negative 1 times the minus 3 that was already there. So now I have negative 10 plus 11I plus 3, and now I can combine these real parts to give me negative 7 plus 11I. You do not need to show all of these steps every time, if particularly this right here. If this is something you can see fairly quickly and you're comfortable, that's something you can do reasonably quickly. Now how about Z squared? On the one hand, I'd like to let you do this one alone, but I do want to give one warning because some of you are still making this mistake. What this is going to mean is it's going to be negative 2 plus I squared. Please remember that you cannot just distribute this squared in. This means negative 2 plus I times negative 2 plus I. So make sure you work through that carefully. So here I'm going to have negative 2 plus I times negative 2 plus I. This gets me 4 minus 2I minus 2I plus I squared. So this is 4 minus 2I minus 2I minus 1. I'm just replacing that I squared with a minus 1. And now we combine like terms. 3 minus 4I. And there we have it. Now there is one more kind of quick conversation that we need to have about multiplying complex numbers, right? The other ones were nice because we only went up to I squared, but what happens when you have higher powers of I? There's a neat sort of pattern thing that happens here that I want to make sure that you're aware of. So we all understand that I squared is negative 1, right? So what about I cubed? Do we get some kind of like super imaginary number when we do this? And the good news is no, we don't. I cubed is just going to be I squared times I. But I squared is negative 1, and so negative 1 times I, well, this is just negative I, right? We don't need some new, weirder imaginary number like a capital I or something for this. We can combine some of the lower powers to work through this. So what about I to the 4th? Well, what would be a really convenient way of thinking about I to the 4th? I mean, I think the most convenient way would be to see it as I squared times I squared. That would be negative 1 times negative 1, which is positive 1. So if you take an imaginary number and raise it to the 4th power, you actually just get back to positive 1. So what about I to the 5th? Well, we could think about I to the 5th as being I to the 4th times I, but we just learned that I to the 4th was 1, and I is just I, so this is I. So what if we did some high power, like I to the 13th power? I'd encourage you to sort of think about that for a moment and consider how you would come up with this. Hopefully you realize that one of the easiest ways to do this would just be to group together, groups of 4 i's, because we know that each one of these is just going to turn into 1, and then we would just have 1 I left over. This is 1 times 1 times 1 times I. This is just I. And so you can even do this for, like I to the 402nd power. Oh my goodness, this would be I to the 4th power, 100 of those, and then there would be 2 i's left over at the end. Well, this is just an incredibly fancy way to say 1, and I squared, we remember from before, was negative 1, And so I to the 402nd power is negative 1. Remember when I first learned this part, this was just really fascinating to me, that it didn't matter what power you raised I up to, it always just ended up being some expression of I or some other real number. So at this point, we're done talking about multiplication and we're ready to move on and talk about other operations. The next operations that I'd like to talk about are division and roots. And the reality is that division and roots are definitely possible, but they're a little more complicated. And in order to understand those, we need to understand a little bit more about complex equations. So I have this guiding principle, right? The guiding principle that we have is that every complex equation is basically made up of two separate equations. There's one that's made up of the real parts and one that's made up of the imaginary parts. And to help you to see that, I want to look at a really fairly simple example. Imagine that I told you that A plus 5i was equal to 3 plus bi plus b, and asked you to find the values of a and b. Okay? The idea here is if these things are going to be equal to one another, the real parts have to be equal and the imaginary parts have to be equal to one another, right? For instance, this 5i right here is the only imaginary part on the left-hand side, and the bi over here is the only imaginary thing on the right side of the equation, which means that 5i has to equal bi, which basically means that b has to be 5. Like, there's no way that b could be anything else. This 3 right here is real. It can't have any effect on the imaginary value of this thing right here. Okay? And if I have that, I should also be able to say, well, a is the only real thing on the left-hand side, so what does a have to be equal to? A would have to be equal to the real things on the other side, 3 plus b. But we just found out that b was 5, so a has to be 3 plus 5, which means a would have to be 8. So do you sort of see how every complex equation is sort of like secretly hiding a system of equations, a real equation and an imaginary equation that both have to be satisfied in order for this complex equation to be valid? Now, this was sort of a simple example. We're going to get into some of them that are a little bit more complex next, so let's do that. So here I'm asking you to find the real numbers a and b such that the quantity a plus bi times the quantity 3 minus 2i is equal to 5i plus 1. So one thing I do want to be really, really clear about is this does not mean that you can just say, ooh, the real part and the real part equals the real part. Yay! So 3a equals 1. This would be really, really wrong. Right? In order to do this, I'm going to need to expand the left-hand side. I'm going to need to really see all of the complexity that's here before I can make these things equal to one another. So the first thing I'm going to do is I'm going to work with that left-hand side. Let's see what we can do about expanding this times 3 minus 2i. So I'd encourage you to pause the video, do that multiplication, give this as an opportunity for yourself to practice it. And if you want, finish the rest of the problem. If not, we'll go through that together. So when I expand this, I'm going to get a times 3. So this is 3a minus 2ai plus 3bi minus 2bi squared. Whew, okay. So these things here are clearly imaginary parts. This thing at the end, we're going to remember, is going to become negative 2b times negative 1. So this is plus 2b. So here I effectively have 3a minus 2ai plus 3bi plus that. Now it might be easier for me if I brought the real parts together, 3a plus 2b, and then after that I could put the imaginary parts, 2ai plus 3bi. And we know that has to be equal to the other side, which is 5i plus 1. And I kind of color-coded these things, right? The idea is that this real part has to equal the real part, so 3a plus 2b has to equal 1, and the imaginary part here has to equal the imaginary part here. In other words, negative 2ai plus 3bi has to equal 5i. I don't really want to keep these imaginary numbers around. Let's just make this 2a plus 3b equals 5. And now what I effectively have is I have a system of equations. I just need to solve this using either elimination or substitution, whatever your preferred method is. You guys know I'm a fan of elimination here, so I'm going to double this one. 6a plus 4b equals 2. and then I will triple this one. So I doubled this one, I'm going to triple this one. Negative 6a plus 9b equals 15. Adding these things up, I get 13b equals 17, so b is 17/13. Maybe not my prettiest answer, but there it is. And then for the other one, let's see here. I think I want to do this one by elimination also. This one I'm going to do by multiplying this equation now by 2. So I'll have negative 4a plus 6b equals 10. And then this one here by negative 3. So that would give me negative 9a minus 6b equals negative 3. Combining these things, negative 13a, these cancel out, equals 7. So a is negative 7/13. Okay, and so what we did here is we solved this, right? We found the values of a and b that made that equation true. Okay, we're going to take that on and practice it in one more place. This problem is really, really similar to the last one. I'm just asking you to find the real numbers a and b such that this equation is true. Please pause the video, expand the left side, and then set the real and imaginary parts equal so that you can solve. So on the left-hand side, I'll have 2a plus ai plus 2bi plus bi squared. And that bi squared, this I squared is going to turn into negative 1. So this whole last term is really just going to turn into minus b. This is going to have to equal 2a minus b minus 1i. And I want to take a look over here on the right. We can tell that this is real. And because b is real, this whole front parentheses is real. So all of this is imaginary. So now what I'm going to do is I want to go back and sort of look at what are the real and the imaginary parts on the left. 2a is real and negative b is real. And the imaginary parts are ai and 2bi. So if we set our imaginary parts equal, ai plus 2bi is equal to negative b minus 1i. And the real parts, I've got 2a minus b on the left and 2a on the right. Well, this actually works out really great for us. These two a's effectively cancel out. I get that negative b is 0, which means that b has to be 0. But if b is 0, it means I can take it and apply it over to this side of the equation, right? Over here, I'm going to have ai, this vanishes, equals negative 1i. In other words, positive I. So ai equals I, which means a has to be 1. Right? So again, we found the values of the real numbers a and b that make that equation true. So now that we have some tools for how to solve complex equations, we can look at how division of complex numbers works. And it turns out that down the line, we're going to learn another method that's a little bit quicker for dividing complex numbers. But this is a good way to look at it now, and it's still really valid. Like even when we learn that other method, this one still has a lot of value. What I'm going to do here is I'm going to say, I really believe that when I divide one complex number by another one, it's going to be equal to some other complex number. So I'm going to say, I know that this is going to equal x plus iy. I don't know what x and y are, but I know that that's what it's going to be, right? And so because I know that and I trust that, I'm going to take this and I'm going to solve it. I'm going to solve this by multiplying both sides by 2 minus I, by the denominator of this over here. When I do that, on the left-hand side, that 2 minus I is going to cancel out, leaving me with just 1 plus 3i. And on the right-hand side, I'll have x plus iy times 2 minus I. And if you look at that, I basically have a little complex equation that I can solve just like I did on the previous slide. So pause the video for a moment, work through this, make sure that you can solve it just like you did before. We're going to have 1 plus 3i over here. On the right-hand side, I'll have 2x minus xi plus 2iy minus I squared y. Well, the I squared is going to turn into negative 1, which is going to make this plus. So I have the real parts 1, 2x, and y. So 1 equals 2x plus y. And then I'm going to have the imaginary parts. 3i equals negative xi plus 2iy. As we did before, we're going to get rid of the i's in the imaginary part. And now I've got two equations with two unknowns. I'm going to solve this as a system of equations, just like I always would. Let's see, I think I'm going to take this one and multiply it by 2 to get the x's to cancel out. Doing that gets me 6 equals negative 2x plus 4y. That means that 7 equals 5y, so y is 7/5. To figure out what x is, let's see here. Oh, it looks like we can just take this equation and multiply it by negative 2 to get the y's to cancel out. So that'll get me negative 2 equals negative 4x minus 2y. Surprise, surprise, the y's cancel out. 1 equals negative 5x, and x is negative 1/5. So now remember, we were trying to answer a very specific question here. We wanted to know what 1 plus 3i divided by 2 minus I was. Well, we just found what x and y were. This thing is negative 1/5 plus 7/5 I. So now that we've talked about how to divide complex numbers, I want to share with you, we can actually take square roots of complex numbers. And we can do it by using the exact same solution method of setting the expression that we want to square root equal to some sort of a general complex number a plus bi, and then solving an equation to find roots. So I'm going to go through this example with you here, right? By writing z as a plus bi, so by writing it as a complex number, I want us to solve this equation. Okay, in other words, we're basically going to find the square root of this because, if I were to sort of square root both sides of this, you can see that what I'm trying to solve for here, what I'm trying to find is the square root of 2 plus 2i root 3. Okay, so the way I'm going to do this is by saying, well, I expect this square root to be something. I expect it to be something like a plus bi, and I expect that when I square that thing, I'm going to get the thing that I'm trying to find the square root of. Okay, so if I expand out the thing on the left, I'm going to wind up with a squared plus 2abi. That comes from getting, a times bi and then bi times a. And then finally, I'll wind up with plus b squared I squared. Okay, now we've seen this enough times. Now this I squared is going to turn into negative 1. So the left side of this is really a squared plus 2abi minus b squared equals the right-hand side. Now I'll give a little bit of warning here. This is it's gonna look like it's getting messy, but it turns out this works out fairly nicely. So stay with me. Don't go running away yet. All right. So just like we did before, what I want to do next is I want to set my real parts equal and my imaginary parts equal. So on the left side, the real parts are a squared minus b squared, a squared minus b squared, and on the right, my real part is 2. For the imaginary parts, on the left, I just have 2ab, and on the right side, I have 2 root 3. I'm leaving out the I this time because our next step is always just to remove that I. Well, this is actually good too. Even these 2's are going to drop out. So really, I just have ab equals the square root of 3. And what I have at this point is I have a system of equations, and I'd like to solve this system. Now, the easiest way to solve this would probably be by substitution, and I'm kind of looking at this going, man, I really wish these were a squareds and b squareds, because then I could just solve this one for like a squared equals b squared plus 2, and like if this thing was an a squared, I could just take this and plug it in right there. So my thinking is, all right, let's just square the blue equation. If I square both sides, a squared plus b squared would equal 3. That even gets rid of the radical part. That seems nice. And so now let's do what we said we were going to do. Let's take that b plus 2 and plug it in. Or sorry, b squared plus 2. So b squared plus 2 times b squared equals 3. All right, I'm going to need to keep working through this. I know that I generally solve things by sort of like getting them equal to 0 and then using the zero product property. So I'm going to distribute this through, get b to the 4th plus 2b squared minus 3 equals 0. And this may seem wild, but this is really just one of those quadratic forms. If I let m be b squared, then this problem is really just m squared plus 2m minus 3 equals 0, which is really easy to factor. This is just m plus 3, and m minus 1, which means that either m is negative 3 or m is 1, but m was b squared, so b squared is negative 3 or b squared is 1. Well, here's the thing. Way back at the beginning of the problem, we said that a and b were supposed to be real numbers, which means b squared can't be negative 3 because we're only working with real numbers. I know this is the imaginary number unit, but we said it was supposed to be real, which means that b has got to be positive 1 or negative 1. So now if I take those things back up and put them into this other equation, what I'll find here is that a squared is 1, because it doesn't matter whether I put in, positive or negative 1 and square it, plus 2. So a squared is going to be 1 plus 2. A squared is going to be 3, which means that a has to be plus or minus square root of 3. And so what that means, if we went all the way back to the beginning of the problem, right? Remember, we were supposed to try and figure out what the square root of 2 plus 2i root 3 was. Well, we just found out that it was a plus bi, which means that it's plus or minus the square root of 3 plus or minus 1i. In other words, it's root 3 plus I or negative root 3 minus I. So this is a long process to find the square root of a complex number, but I want to show you that it's possible. We will be learning other ways to do this as we get further into the class, but we need to build up a lot more machinery before we get there. So this is the tool that we have at the moment. So I know that there are several minutes left in the video, but at this point I'm done covering everything that needs to be covered. What I'm going to do in the rest of the video is just go back and do another example of division and another example of a root. So if you need to see more of those, please feel free to move forward and check those out. If at this point you feel good with it, you've got a strong sense of what's going on and you're ready to go try the work, by all means do that. As always, if you all have questions, make sure that you ask, and I wish you best of luck as you work through these problems. And I really, really am excited for what we're about to learn about complex numbers. So best of luck. As promised, I have here another example of a division problem, division of two complex numbers. So if you'd like to try this one on your own, go for it. You'll get a chance to see me work through it. If you just need to see another one worked, here we go. My strategy is that I'm going to say, I know that this has to equal a complex number, x plus iy. And so I'm going to go ahead and write it there. Okay. My next step then is to multiply this 3 plus 4i over. And so when I do that, I wind up with 5 minus 10i equals the quotient that I'm trying to find times the denominator that I just multiplied over. Okay. In order to work this out, I'm going to need to expand the right-hand side. So I'm going to get 3x plus 4xi, and then here plus 3yi, and then finally plus 4yi squared. We've noted that the I squared becomes negative 1, and so really the right-hand side here becomes 3x plus 4xi plus 3yi minus 4y. And our left-hand side is still 5 minus 10i. Okay? Remember that our strategy in working with these complex equations now is to bring the real parts together. 5 has to equal 3x minus 4y. 5 has to equal 3x minus 4y. And then the imaginary parts. Negative 10 has to equal 4x plus 3y. And remember, you can sort of just drop the imaginary parts out of them because each of them has the exact same factor of I. If it didn't have it, it would be real. And if it was a higher power of I, you should have simplified it earlier. Okay. So now that I'm here, I need to solve this. So I'm going to do this by elimination. I'm going to multiply this first equation by, let's get rid of the y first. So I'm going to multiply this one by 3. Doing that's going to get me 15 equals 9x minus 12y. And then I'll multiply this one by 4, because that'll make the y's sort of cancel out. So negative 40 equals 16x plus 12y. And these are big numbers. I'm really hoping this is going to work out nicely for us. On the left side, this is going to simplify down to being negative 25. On the right side, I have 25x, and these drop out. Well, that was really nice. X is negative 1, right? So now, I mean, I don't even know that I need or want to do substitute or elimination for this. Let's just put this back in. When I plug this thing back in, I wind up with negative 10 equals negative 4 plus 3y. That means that negative 6 equals 3y, so y is negative 2. And now that I have these two things, I've effectively found this complex number. Remember, it was x plus yi. So this is basically negative 1 minus 2i. So we just learned that 5 minus 10i divided by 3 plus 4i gives me this negative 1 minus 2i. So this is currently our only method for dividing complex numbers. As promised, I'm going to go on and do an example of the root of a complex number next. So in this next one, we're going to find two values of the square root of I, which is really neat because it's a very sort of specific and interesting example for us. So the square root of I, if I was going to do this, I would need to say, well, the square root of I needs to be a complex number. Now that I have that, I'll proceed with squaring both sides so that I wind up with I equals x plus iy times x plus iy. And now I'll expand out that right-hand side. This is going to get me x squared plus xyi plus another xyi, and then finally plus y squared I squared. Okay, let's simplify that right-hand side a bit. This is x squared. These are going to come together to give me 2xyi, and this at the end is going to become minus y squared because that I squared becomes negative 1. Now, just like we've done in the past, I'm going to go and set my real parts equal and my imaginary parts equal. So the imaginary parts first. The imaginary part on the right-hand side is 2xy, and the imaginary part on the left-hand side is just I, so I'm going to put 1 there. Now, the real parts are a little bit funky. On the right side, my real parts are x squared minus y squared. What's the real part on the left? The real part on the left is actually 0, which actually makes this example easier to do than the one that we did previously, right? I'm going to solve this by saying that x squared has to be equal to y squared. And if x squared equals y squared, I think I should be able to bring that knowledge over to here, right? If I square both sides of this, I'll get 1 equals 4 x squared y squared, which means 1 is 4 x squared x squared. So 1 is 4x to the 4th power. So now to solve this, I'm going to want to divide that 4 over. So 1/4 equals x to the 4th power, and then we can 4th root both sides. So you're kind of running out of space here, so let's keep going. So the 4th root of both sides, so this would be x is, the 4th root of 1 is 1. The 4th root of 4 is basically the square root of 2. So this is going to be plus or minus 1 over the square root of 2. So we just found that x is plus or minus 1 over the square root of 2. And to find y, I just want to plug it back into this, right? If we know that 1 equals 2xy, 1 would equal 2 times plus or minus 1 over root 2y. So that means that 1 is plus or minus 2 over root 2y. This will actually simplify down to being plus or minus root 2y. And then the last thing I need to do is divide that root 2 over. So I get that y is also plus or minus 1 over root 2. So what we had stated at the very beginning of the problem was that the square root of I is x plus iy. So we have just found that the square root of I is 1 over root 2 plus 1 over root 2i, or the square root of I is negative 1 over root 2 minus 1 over root 2i. And I might sort of mention one more thought here. So that means that the square root of I is actually plus or minus 1 over root 2 plus 1 over root 2i. So we sort of still even have this idea that when we take the square root of something, we're winding up with plus or minus something. And that's a neat sort of symmetry to see. If you're still watching all the way to here, you've gone through a lot of this. And so I really, really, really hope that this has all been clear. As always, if you still have questions, please reach out and ask me. I would love to talk to you about this. So best of luck as you work through the assignment.